Okay, so this is problem 8.6.37, and we're finding the partial fraction decomposition. And anytime you're finding the PFD, the first thing you have to do is factor the denominator of the expression you're working with first. So if we take a look at the bottom, and I go to factor this, I see I'm going to try a 4x and a 4x, and a 5 and a 5, and I notice that if I put both plus signs there, that will work for this factorization. Outside and inside give me 40. Okay, so if I were to write this to show the repetition in the factor here, this is actually 4x plus 5 as a quantity squared. Okay, so what we want to do, this is a linear factor that is repeated. So when we go to set this up, this is case 2. Remember that there are 4 cases when you're working with partial fraction decomposition, and you need to be able to identify which case the denominator is in order to be able to know how to set it up. Okay, so this particular problem, because this is a repeated linear, we're going to set it up this way. We're setting it equal to a over 4x plus 5, and then b over 4x plus 5 squared. Okay, so this is case 2. And so go back, and if you don't know what I'm talking about, you should definitely go back and listen to the lecture on these and review the different cases for setting them up based on what the denominator looks like. Okay, so at this point then, what I'm going to do is clear the fraction. So I'm going to multiply both sides by 4x plus 5 quantity squared. And that's going to allow me to set up an equation here. So I'll be left with 20x plus 22 on the left-hand side. And then here, this 4x plus 5 squared is getting distributed, so it's multiplying this and this. When I multiply it times a over the 4x plus 5, one of the 4x plus 5s will cancel, and I'm going to be left with another one. Okay? And then here, both of them will actually cancel, and I'll just be left with b. Okay, so in this particular example, I think it's probably easier to solve from here if we distribute the a and then if we equate component pieces. So if I say 20x plus 22 here, if I distribute the a, I have 4ax plus 5a plus b. Okay, now because I have 4ax equaling 20x, since there's a 4a piece over here and there's a 20 over here, then I can set the 4a equal to 20 because of this equal sign here, whatever's on this side should equal this side. Well, if I have just one component here that has an x, then it has to be equal to this coefficient over here for x has to be equal to whatever the coefficient is over here. So that means 4a has to be equal to 20. I can pull that off as an equation, and that allows me to solve and find a is equal to 5. Okay, so this is one of the ways to solve these. The other way is to do the let x equals method, where you let x equal a certain number and plug it in and, solve it. But this one's easier in this way. So a is equal to 5, and then to find b, this is a constant and this is a constant, and that should equal the constant on the other side. So the second equation here is 5a plus b is equal to 22. Now, I already found what a is, so I can plug that in here. I have 5 times 5 plus b is equal to 22. So this is 25 plus b equals 22. And when you subtract your 25 to the other side, you're going to get b is equal to a negative 3. Okay. Now remember, with partial fraction decomposition, you always want to go back and assemble your fraction to answer the question. So since this is equal to a, we found a to be 5 and b to be negative 3. We're going to plug those in there, and this partial fraction is going to be equal to 5 over 4x plus 5, and then plus negative 3 over 4x plus 5, the whole thing being squared. Okay, so that would be your answer in this particular problem. Okay, and then another question was also asked again on the partial fraction decomposition. This was problem 8.6.47. Same directions here. We're finding the PFD. Okay, and here is the problem for this one. Okay, so this one is actually a case 3 partial fraction decomposition for the bottom. I see that I have irreducible quadratics. So the way that we set those up is we say ax plus b over my x squared plus 7, and then I'm going to have a cx plus d over my x squared plus 8. Okay, and now we're doing the same thing. Once we've done the setup, we want to clear the fraction. So I'm going to multiply both sides by the LCM, or the common denominator, which is x squared plus 7 times x squared plus 8. Okay, so over here those cancel, and we're left with 8x squared plus 9x. On this side, the x squared plus 7's will cancel, and I'll be left with an x squared plus 8. So, oops, that's a b. So I have ax plus b times x squared plus 8. And then here, x squared plus 8's will cancel, and I'm left with cx plus d times x squared plus 7. Okay, so at this point, I don't think it's going to be very easy to, well, let's look at it. If we equate component pieces here, that might work. Yeah, let's try equating component pieces. It might end up being a monstrosity of a problem, but if it is, then we'll just try the other way. So what I'm going to do here is multiply this out. It's FOIL. So this is ax cubed plus 8ax plus bx squared plus 8b. Okay, and then I'm going to do the same thing here. I'm going to multiply this out. So this is cx cubed plus 7cx plus dx squared plus 7d. Okay, now component pieces here, if I take my cubes, I have an a and a c. There's no cube over here. So my equation that's going to come out of this is, the first equation that I can find is a plus c is equal to 0, because whatever the coefficients are here should equal the coefficient of the cube over here, and there is no cube. So that means my a plus c has to equal 0. Okay. If I look at the squareds, I've got a b squared, a bx squared, and a dx squared, and I have an 8x squared over here. So that means that my b plus my d has to equal 8. Okay. All right, so those are gone. Third equation here, I can pull off for the x's. I have 8ax and 7cx. So my 8a plus my 7c should equal over here 9. Okay. And then I see the fourth equation here. I have 8b plus 7d. Those are constants. That should equal the constant over there, which is 0. Okay, so this is actually solvable, because in this first equation here I can see that a is equal to negative c. That's just solving it for a, subtracting the c to the other side. And then I can take this negative c and I can plug it into my third equation to solve for c. So this becomes 8 times negative c plus 7c is equal to 9. So this is negative 8c plus 7c. That's a negative c equals 9. So in other words, c is equal to negative 9. Okay, once we've found c, then we can find a, because a is just the opposite of c, so a here is a positive 9. Okay, and then I'm going to work with equation 2 and equation 4 to try and get a solution for b and d. So this system of equations, we have b plus d is equal to 8, and then we have 8b plus 7d is equal to 0. And you can solve that by substitution or elimination, whatever you would like. I think I'm just going to go ahead and solve it by elimination. So I'm going to multiply this top one here by negative 7. So that's going to give me a negative 7b, a negative 7d, and a negative 56. And that's going to allow me to add these two equations, and the d's will cancel, and I'm left with a positive b equaling negative 56. Okay? And then once I know that, I can plug b back into either of these equations. If I plug it back into the equation b plus d equals 8, then I have negative 56 plus d equals 8, and add your 56 here, and so you get 64. Oops. Okay. All right, so then we can reassemble our partial fraction decomposition. It's going to look like this. It was this over here, ax plus b, and then cx plus d. So the a is, we found a to be 9, so we have 9x minus 56 over x squared plus 7. And then we have plus, the c is negative 9x, and then d is 64, all over the x squared plus 8. Okay, so that would be your answer on that one.